We can tell whether an object will speed up, slow down, and or turn at a given moment by looking at the angle between its velocity vector at that moment and its acceleration vector at that moment. If the angle is obtuse, greater than 90 degrees, then we know the object will slow down in the next few instants and turn towards the acceleration. That means that the velocity vector will be tipping to point more and more towards the same direction that the acceleration vector is pointing. So it'll slow down and turn if that angle is greater than 90 degrees. If the angle is acute, less than 90 degrees, then the object is going to speed up and turn towards the acceleration, continue to tip towards that acceleration vector over time. And if the angle happens to be exactly 90 degrees, then the object will neither speed up nor slow down at that moment, but it will turn. That velocity vector is about to tip towards the acceleration vector in that instant. According to Newton's second law, though, the acceleration vector is always parallel to the net force vector on an object at a given moment. They're always pointing the same direction, which means that rather than comparing the angle between acceleration and velocity at some instant, we could instead compare the angle between net force and velocity at that instant, since that we'd be talking about the same angle. So 5 cases here. If that angle is 180 degrees, if the net force points exactly opposite the velocity, that's of course going to cause the object to slow down. That force is slowing the object down, but there will not be any turning if they're exactly opposite. If the angle is between 180 and 90 degrees, so an obtuse angle, but not exactly opposite, that force pushing kind of away from the velocity is going to cause the object to slow down, but also turn. The velocity vector will tip towards that net force vector over time. If the angle is 90 degrees between net force and velocity, neither speed up nor slow down, simply tilt towards net force. For an acute angle greater than 0 degrees, we'll speed up and turn. And if the angle is 0 degrees, if the force is pushing exactly with the velocity, then we'll simply speed up without turning. Furthermore, looking between 2 different moments in time as an object moves along a path, if the net force on the object happens to be constant between those 2 moments, you can then use the angle between net force and average velocity to compare the initial and final speeds, v1 and v2. And now, since average velocity is defined as displacement vector over time, then average velocity and displacement are always parallel vectors. So we can compare the angle between net force and displacement to get that same information. So here's 3 scenarios where this dwarf miner here is tossing a gem to his pal. The moments 1 and 2 are marked. And we see the gem here, while it's in the air, is following this parabolic path. The net force on it is only the force of gravity. And we've drawn in the displacement vector, delta r, pointing from the location of the object at moment 1 to the location of the object at moment 2. And we're going to look at that angle between net force during that whole time, assuming it's a constant net force that whole time, and the displacement vector. So if they are roughly against each other, that is an angle that is obtuse, greater than 90 degrees, then the object at moment 2 will be slower than it is at moment 1. We know here at 2, the gem will be slower than it is here at 1. In the next case, if we're looking at 2 moments, 1 and 2, where the gem has returned to the same height from which it was, we know that the object will have the same speed at those 2 moments. So if that angle is 90 degrees, a right angle between net force and displacement, then the speeds will be equal at those 2 moments. Third case, if our second moment has the object down here lower than where it was at moment 1, that is, if it makes an acute angle between displacement and net force, then the speed at 2 is guaranteed to be greater than the speed at 1. All right, that's the idea. Practice this yourself. Here are 8 scenarios. In each case, I've only shown you the net force vector on the object and the displacement vector between 2 moments in time. You're not shown the path of the object or any other information, just those 2 vectors. And with that information alone, can you determine whether its final speed will be greater than, less than, or equal to its initial speed? Go ahead and assume it's a constant net force in all these cases. So in a moment, you're going to pause the video and come up with a comparison between those 2 speeds for all 8 of these moments. Pause the video now. Ready? Here's the result. The final speed will be greater than the initial speed in cases B, E, and H, since those cases have an angle between net force and displacement that is acute, meaning that the net force pushes roughly with the direction of motion, speeding the object up overall between those 2 moments. The final speed will be less than the initial speed in A, F, and G, since in those cases, A, F, and G, the angle is obtuse, the net force pushed roughly against the displacement, slowing the object down overall between those 2 moments. And the final speeds will be equal in cases C and D, since that 90-degree angle, that right angle between net force and displacement, results in neither an increase nor a decrease in speed.